For centuries, the Akashi Strait was one of the most feared stretches of water in Japan. Locals called it a graveyard. Fishermen knew its currents. Sailors respected its storms. And anyone who had to cross it, merchants, travelers, families, understood that the sea between Honshu and Awaji Island did not forgive mistakes. The strait is only about 2 miles wide. On a calm day, you can see the other side. But the Akashi Strait is almost never calm. Powerful tidal currents run through it at speeds that can flip small vessels. Typhoons arrive from the Pacific and funnel straight through the channel with almost nothing to slow them down. And beneath the water, the geology is deeply unstable. This region sits at the collision point of 3 of the most active tectonic plates on Earth. The ground here does not sit still. It shifts, it trembles, and occasionally it tears apart with catastrophic force. The human cost of this crossing had been building for generations. In 1955, 2 ferries sank in the strait during a sudden storm. Over 160 people died, most of them children returning from a school trip. The nation was shaken. People demanded a solution. Politicians talked about a bridge. Engineers quietly stared at the numbers and wondered if such a thing was even possible. Because the Akashi Strait is not just dangerous, it is one of the busiest commercial shipping lanes in Japan. Any bridge would need to allow massive cargo vessels to pass beneath it. That meant the main span had to be enormous, far longer than any suspension bridge ever built. It meant the towers would have to rise higher than almost any structure on the Japanese coastline, and it meant the entire system would have to survive not just wind and waves, but earthquakes powerful enough to level cities. Japan had already lived through enough disaster to know what was at stake. The 1923 Great Kanto earthquake killed over 100,000 people. The country had rebuilt. It had modernized. But every engineer who looked at the Akashi crossing understood that building here meant accepting a terrifying constraint. The bridge could not simply be strong. It had to be strong enough to survive the worst event that nature might throw at it, and then keep standing for 100 years after that. That was the problem. And for a long time, no one was sure it could be solved. Before a single cable could be stretched across the Akashi Strait, engineers had to solve a problem that had no clean answer. How do you plant 2 massive towers into the floor of an active, fast-moving, seismically unstable sea, and trust that they will never move? The water in the strait reaches depths of nearly 200 feet in places. The currents run so strong that construction divers could only work in short windows between tidal shifts. The seabed itself was a layered mixture of sediment, gravel, and rock that varied unpredictably from one location to the next. There was no simple foundation waiting beneath the surface. Everything had to be created from scratch, underwater, in one of the most hostile marine environments in the country. Engineers designed 2 enormous concrete caissons, hollow cylindrical structures that would be built on land.
Each caisson is the size of a baseball stadium, built to anchor the towers.
Floated out into the strait, positioned with extreme precision, and then sunk onto the seabed. Each caisson was roughly the size of a baseball stadium footprint. Once in position, they were filled with concrete until they locked permanently into the ocean floor. On top of each caisson, the bridge towers would eventually rise nearly 1,000 feet into the sky. Getting those caissons into exactly the right position was an engineering operation that required GPS-level accuracy in an era when GPS was barely available. Survey teams used laser measurement systems and constant monitoring to guide each caisson into place.
Precision was key. Even a small error could misalign the entire bridge.
Even a small error in positioning would throw off the geometry of the entire bridge, the cable angles, the span lengths, the load distribution across the structure. Everything depended on those 2 foundation points being exactly where the calculations said they needed to be. Then, in 1995, the ground moved. While construction was underway, the Great Hanshin earthquake struck the region with a magnitude of 6.9. It killed over 6,000 people. It collapsed highways and flattened entire neighborhoods in Kobe, just miles from the construction site. And when engineers rushed to inspect the bridge foundations, they discovered something that would have ended almost any other project in the world. The earthquake had shifted one of the caissons, not by much, roughly 3 feet, but 3 feet on a structure of this scale changes everything. Span calculations, cable lengths, tower alignment, all of it had to be recalculated from the new position. The project did not stop. Engineers adjusted. They rebuilt their models around the new reality and kept going. That decision said everything about what kind of bridge this was going to be. Most people look at a suspension bridge and see something rigid. 2 towers, a roadway, cables running in long, graceful curves from one end to the other. It looks permanent. It looks fixed. It looks like something that does not and should not move. That intuition is completely wrong. And for the Akashi Kaikyō Bridge, that wrong intuition could have been fatal. A structure that refuses to flex under extreme force does not survive. It fractures. The history of engineering is full of bridges that were too stiff, too proud, and too confident in their own rigidity, until the wind or the earth reminded them what happens to things that cannot bend. The Tacoma Narrows Bridge in Washington state collapsed in 1940 under winds that were nowhere near catastrophic. It did not break because it was weak. It broke because it resonated. It caught the wind's frequency like a tuning fork and shook itself apart. Japanese engineers knew that story well. They also knew they were building in a place where the wind regularly exceeds 180 miles per hour during typhoons, and where the ground beneath the strait can shift without warning. Rigidity was not an option. The bridge had to be designed to move. The main cables alone contain enough steel wire to circle the Earth 7 times. Each cable is nearly 4 feet in diameter, made from thousands of individual high-strength steel wires bundled and compressed into a continuous strand running from one anchorage to the other. Cables do not simply hold the bridge up. They distribute the load across the entire structure, transferring weight dynamically as traffic patterns shift.
These cables hold the bridge, adjusting as traffic and temperature change.
As temperature changes alter the steel's length, and as wind pushes against the roadway deck. The deck itself was engineered with aerodynamics in mind. Wind tunnel testing revealed that the original truss design created dangerous turbulence at high speeds. Engineers modified the cross-section, opening gaps in the structure to let wind pass through rather than push against a solid surface. The bridge does not block the storm. It lets the storm move through it. At the top of each tower, the structure can sway several feet in either direction during a powerful typhoon. The roadway can shift horizontally. The cables can change their angle of tension. All of this movement is calculated, expected, and accounted for in every bolt and joint throughout the system.
The bridge sways with the wind, designed to move, not resist.
This bridge does not stand still. It breathes. And that is precisely why it is still standing. When Japanese engineers sat down to define the survival requirements for the Akashi Kaikyō Bridge, they did not ask what conditions the bridge was likely to face. They asked what conditions the bridge could never be allowed to fail in. That distinction changed everything about how the structure was designed from the inside out. The official seismic target was a magnitude 8.5 earthquake, not the kind of earthquake that cracks walls and breaks windows. The kind of earthquake that reshapes coastlines. The kind that, in Japanese history, has killed hundreds of thousands of people in a single morning. Engineers had to look at that number and design a bridge that would still be standing and still be functional on the other side of it. To achieve that, the internal systems of the bridge became as important as the visible structure. Inside each of the 2 main towers, engineers installed massive pendulum dampers, heavy steel weights suspended on long cables within the tower walls.
Pendulum dampers swing to counteract seismic forces, a crucial innovation.
When the ground shakes or the wind pushes, The pendulums swing in the opposite direction of the movement, counteracting the force before it can build into something dangerous. The towers do not simply endure the energy of an earthquake. They actively push back against it. The foundation caissons were designed with the same logic. Rather than anchoring rigidly to the bedrock and hoping the rock never moved, the foundations were engineered to absorb and redirect seismic energy. The concrete mix, the depth of penetration, the shape of the base, all of it was calculated to give the structure a controlled response to ground movement rather than a catastrophic one. Wind was treated with equal seriousness. The bridge was tested extensively in one of the largest wind tunnels ever built for a civil engineering project. Models were subjected to simulated typhoon conditions at speeds far beyond what weather records suggested was the realistic maximum. Engineers wanted to know not just where the design would hold, but exactly where and how it would begin to fail, so they could reinforce those points before construction began. The electrical systems, the monitoring networks, the maintenance corridors built inside the cables themselves, all of it was designed around one central idea. This bridge would face disasters. Not might face them. Would. The question was never whether the worst day would come. The question was whether the bridge would still be there the morning after. Every answer the engineers gave pointed toward yes. On April 5, 1998, the Akashi Kaikyō Bridge opened to traffic. No earthquake stopped it. No typhoon delayed it. No engineering failure forced a redesign. After nearly a decade of construction, one of the most seismically active and meteorologically violent stretches of water in the world had a bridge crossing it. And that bridge held a record that still stands today, the longest suspension bridge span on Earth, stretching 6,532 feet between its two main towers. The numbers are almost impossible to visualize. If you placed the main span vertically, it would be taller than any building in the Western Hemisphere. The towers rise 928 feet above sea level. The bridge carries 4 lanes of traffic and was built to last at least 200 years under the conditions of the Akashi Strait. Engineers did not build for the present. They built for generations of people they would never meet. For the communities on Awaji Island, the change was immediate and profound. A crossing that once required a ferry, subject to weather cancellations, limited schedules, and the ever-present risk of the strait itself, became a 12-minute drive. Families separated by water were suddenly neighbors. Businesses that could never reliably move goods across the channel had a permanent, all-weather connection to the mainland. The island's economy began to shift within years of the opening. But the significance of the Akashi Kaikyō Bridge extends far beyond Japan. Engineers and governments around the world studied what had been built here. The construction techniques developed for the caisson foundations influenced offshore projects globally. The aerodynamic deck design became a reference point for suspension bridges built in high-wind environments from Europe to Southeast Asia. The seismic engineering logic embedded in every damper and joint gave other countries a framework for building critical infrastructure in earthquake zones. When you drive across the Akashi Kaikyō Bridge today, the experience is quieter than you might expect. The roadway is smooth. The towers disappear into the sky above you. The strait moves beneath you, cold and fast, and completely indifferent to the structure spanning it. You are crossing 2 miles of open water on a bridge that survived a major earthquake during its own construction, was redesigned around the damage, and opened on schedule anyway. That is not just an engineering achievement. That is a specific kind of human stubbornness, the refusal to accept that some problems are simply too hard. Japan looked at the most dangerous crossing it had, decided that was exactly where the bridge needed to go, and built something the world had never seen before.